Hi everyone. In this lesson we're going to discuss conditional convergence and absolute convergence. So these are two different types of convergence that we'll be able to classify series into. Now before we get into the details of the definition for these, we need this theorem first. So this theorem makes the following statement. If we're given any sequence a sub n, now this can have positive or negative numbers in it, it doesn't matter. If the series involving the absolute value of the a sub n terms converges, then the series of just the an terms without the absolute values must also converge. Now let's take a look at the proof of this theorem, and then we'll talk about conditional versus absolute convergence. So to prove this theorem, we want to prove that if this is true, then this must be true. So the way we do that is we assume that the series of the absolute value of the an converges, and then through logic and mathematical results we must show that this holds. So we assume that this is true, so that the series involving the absolute value of the an terms converges. We must argue that this series converges as well. Okay, so to do that, first of all, take note of this. It's certainly true that if you look at the an terms, just pick any an out of the sequence, that is going to be bigger than or equal to negative the absolute value of itself and less than or equal to the absolute value of itself. So this is certainly going to hold. For example, if consider the number -3. It's most certainly true that -3 is bigger than or equal to negative the absolute value of -3. And less than the absolute value of -3, right? Because this right here would just be negative of 3, so that's -3. So because we have less than or equal to here, negative 3 is greater than or equal to -3. And this over here is just 3, right? So if you take a number like -3, most certainly this holds. On the other hand, if you have +3, this will still hold. For example, if you have +3, just note that +3 is bigger than or equal to negative the absolute value of 3, right? Because this is -3. And it's also less than or equal to the absolute value of itself, which is just 3. Okay, so you see this holds as well. Okay, so most certainly this is true. Now let's note that we can manipulate this a little bit. We're just going to add absolute value of an to each term in this inequality. So just, plus absolute value an for each one, right? This side, the left side, is going to be 0 then. The middle term becomes an plus absolute value an, and this will be 2 times the absolute value of an. Okay, so we get that. Now, since we're assuming that this series converges, then this series we can write as 2 times. We can just pull the 2 out like that. It will also converge, right? We're just multiplying each of these terms by a 2. We can move the 2 out in front of the summation, so certainly this will be a convergent series. Now let's also note from our inequality here that since the series involving these terms converges, the series involving these terms will also converge by the domination test. So this series will converge by the domination test that we looked at previously. Okay, and that's because of this inequality right here. Now let's also note that we can write this series that we're trying to show converges, we can write it like this. We can write it like this right here. You notice that these absolute value ANs just cancel, so we use that little math trick, add in, subtract back out. Now we can also write this, we can distribute the summation and write it like this. Now we know that this series converges, that we assumed, we were given that, and we also deduced that this series converges. Therefore we know now that this series must converge because it's the difference of two convergent series. And there you go, we've completed our proof. Okay, so now that we have this result, let's take a look at the definition for conditional convergence and absolute convergence. So here's our definition, and it simply goes like this. A series, sum of a sub n's, is said to converge absolutely if this series converges. In other words, since this is true, if this converges, then both this series and this series converge by the previous theorem that we just looked at, right? Okay. So that's what we mean by a series converging absolutely, if the series of the absolute value of the ANs converges. So that means that both of these series converge. Otherwise, a series is said to converge conditionally if the series of the AN terms converges, but the series involving the absolute values diverges. That's called conditional convergence. Okay, so let's take a look at a few examples that will clarify this definition. Now, before we look at a few examples, please familiarize yourself with these guidelines for determining whether you have absolute convergence, conditional convergence, or divergence. Now, we're going to execute these guidelines in these examples, so please read through these before we go over these examples. So here we have 5 series that we would like to determine the type of convergence: absolute, conditional, or divergence. So let's start with the first one here. So we have the summation from 1 to infinity, -1 to the n plus 1 power divided by n. So that will generate a series that looks like this. Notice the alternating sign pattern that comes from the -1 to the n plus 1 term. And so it just goes 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on. Now the general procedure to determine the type of convergence we have is to first of all look at the summation of the absolute value. If this converges, you're finished, you have absolute convergence, and you're done. If this converges, remember, so does the original series, and that's it. So let's take a look at this. So in this case, this is equal to the sum of 1 over n from 1 to infinity. Okay, now we know that this actually diverges by the p-series test, right? So this diverges. Okay, so we definitely do not have absolute convergence. So perhaps we still have convergence of this series, however, in which case we would have conditional convergence. So what we want to look at next is, since this is an alternating series, perhaps we can apply the alternating series test. So since this series can be written like this, remember with the alternating series test, we want to look at these terms to see if it satisfies the two conditions that we need for convergence. So first of all, does the limit as n go to infinity of 1 over n, does this equal 0? Well, yes it does, right? So that's condition 1 of the alternating series test. Condition 2, are the an plus 1 terms less than or equal to the an terms. Well, in this case, the an plus 1, these are the an terms now, remember. Okay. When we did this up here, we considered the an as being the entire term in this summation, including the -1. But now when we're doing the alternating series test, we restrict the an just to be the positive part. Okay, so it's 1 over n now. Well, we have to determine if this is satisfied. Well, yes, that is satisfied, because most certainly 1 over n plus 1 is definitely less than 1 over n, because we make the denominator a little larger. So this is certainly true. And so there we go. We do have convergence of this series by the alternating series test. So we'll just say that this converges by the alternating series test. Okay, so what we have is that the absolute value of this does not converge, but the series with the -1 in it does converge, so we have conditional convergence. And so we would just say here that this series converges conditionally. Let's take a look at number 2. So once again, our general procedure is to start with the summation of the absolute value of the terms inside the summation. So we want to consider this. Right, that's the absolute value of these terms here, right? The absolute value of this is 1 over n squared, right? Now this does converge by the p-series test. And so since this converges, so does this series without the absolute values as well, by what we've just looked at. And so therefore we have absolute convergence for this series. Okay. Now let's take a look at this one. So for number 3, again, we want to start with determining if we have absolute convergence. So we look at the summation of the absolute value of these terms. And so when we take the absolute value, we get this. Now, that's actually a geometric series, right? Because you can write that as, right? And so our r in this case is 1/2. And this one, we actually know exactly what that converges to, right? That actually converges to 1/2 divided by 1 minus 1/2, right? We actually know it converges to that. So this series does converge with the absolute values, so we have absolute convergence. Let's take a look at this one. So what we have here, so for number 4, once again, let's see if we have absolute convergence. If we have absolute convergence, we're finished. So we consider this first. All right, notice that this is the absolute value of these terms down here. Now, it's not immediately obvious if this converges or diverges. What we need to do here is apply the integral test, actually. So let's consider this. Okay, now notice that we are allowed to apply the integral test with this function because, first of all, the function here, f of x, does satisfy f of n equals an, okay? And also, the other condition that we need to apply the integral test is that this is a decreasing function. Okay, so let's just double check here. If we take the derivative of this function, okay, so applying the quotient rule, what you're going to get is 1 minus the natural log of x divided by x squared. You can double check that. That's just the quotient rule. Just double check that. Now you notice that this is definitely negative, less than 0, for x greater than, actually in this case it would be e, because the natural log of e is 1. So when we put e in here, that's when the numerator is 0. And then as x gets larger than e, the numerator will become negative, right? Because the ln of x will become larger than 1 for x greater than e. So this is going to be a decreasing function, so we can apply the integral test. Okay, so what we want to do here then, we want to evaluate this using substitution, right? So we'll let u equal the ln of x, okay, in which case du is going to be 1 over x dx. And we see that this becomes, let's see, the ln of x is going to be our u. Dx over x, that becomes du. And let's see, what are the limits of integration going to be? Well, when x is 1, ln of 1 is 0. And then as x goes to infinity, so does the natural log of x, right? As x gets larger and larger, so does the natural log. So this is going to remain an infinity up here. Okay, so now it's easy to see that this integral here is going to equal infinity, right? Because the antiderivative of u is u squared over 2. Just very quickly down here, evaluate that from 0 to infinity, right? Put infinity in for the u. Of course, infinity squared is infinity, so yes, this does not exist, okay? Very easy to see that graphically also, because if you look at the graph of y equals u, of course that's an increasing function, so the area under that curve from 0 to infinity is going to be infinite. Very easy to see that. So therefore this does not exist, therefore this does not exist either. So this diverges. Okay, so we've determined now that we definitely do not have absolute convergence. Okay, so this diverges. So at best we're going to have conditional convergence. So what we need to do now is see, well, perhaps we can apply the alternating series test. So let's consider this now. So now if we consider our original series down here without the absolute values. Okay, now if you think back to the alternating series test, these are going to be the an terms that we need to consider. Okay, so let's see. First thing, what is the limit as n goes to infinity of the natural log of n over n? Okay, well, let's see. This is, if we put infinity in for these n's, you see we get infinity over infinity. All right, that's an indeterminate form. We can apply L'Hopital's rule. So applying L'Hopital's rule, this is going to be the limit as n goes to infinity. Derivative of the top is 1 over n. Divided by derivative of the bottom is 1. Well, this is definitely going to be 0. Okay, because as n goes to infinity, 1 over n goes to 0. So condition 1 of the alternating series test is satisfied. Now we need to verify this. Are the an plus 1 terms less than or equal to the an terms, the terms right before them? Well, so we have to look at this. So is this true? Is it true that the natural log of n plus 1 divided by n plus 1, is this less than or equal to the natural log of n over n? That's what we have to determine. Well, we actually already determined that this is true, because if you think back, we considered the derivative of this function, right? We found that that was 1 minus the natural log of x over x squared, and we saw that that is actually a negative function for x sufficiently large. So therefore, ln of x over x is decreasing for x sufficiently large, in particular for x bigger than e. And so therefore, this is true. So we can say right here, yes, that does hold, because this is a decreasing function, because the derivative is negative. So therefore, this does converge by the alternating series test. Okay, so we now have determined that this converges by the alternating series test. Therefore, this series converges conditionally. And there you go. Let's take a look at number 5. Okay, so for number 5, once again, we start by considering the absolute value of that series. So we consider this. If this converges, we have absolute convergence, and we're done. Well, let's see here. This does not look like it's going to converge. This actually diverges, since if we look at the limit as n goes to infinity of these terms, that's equal to 1, which does not equal 0. And so by the nth term test, this must diverge, right? Remember, the nth term test says that if the limit of the an terms does not equal 0, then the series must diverge. Okay, so we have divergence by the nth term test. Okay, so at best we can have conditional convergence at best. So now let's consider the summation of the whole thing here. Let's see if we can somehow show that that converges or diverges. Okay, now since this is an alternating series, because of that negative term, we would hope we could apply the alternating series test, but we can't. And that's because if we remember, the first condition of our alternating series test is that the limit as n goes to infinity of our an terms, this must equal 0. But in this case, it's equal to 1, which does not equal 0. Therefore, we cannot apply the alternating series test. We can't apply. Okay, so now we're sort of back to square one. What do we do with this? Does it converge or diverge? Well, once again, just look, by the nth term test, we can apply that again to this series. Certainly, since the limit as n goes to infinity of n squared over 1 plus n squared is 1, that implies that if we consider this limit, this limit does not exist, right? So a dne, because these terms right here are getting closer and closer to 1, but then the negative 1 makes these values flip-flop between values that are close to negative 1 and then close to positive 1. Negative 1, positive 1, negative 1, positive 1. So this limit does not exist, which, well, that of course means it's not 0. And so once again, by the nth term test, this series actually diverges. So therefore, this series diverges by the nth term test. And so we have concluded now that this series just diverges. We don't have conditional convergence, we don't have absolute convergence, it just diverges. And that concludes this video about absolute and conditional convergence.